morning. Thank you for joining me here today, and thank you for giving me the opportunity to talk about a topic that I am very passionate about. I spent the last number of years working on systems, distributed systems, that are by many measures high scale and high complexity. So we're talking hundreds of microservices, millions of users, and more requests than you can easily count on a few fingers. So over these past few years, I learned a lot of things about what it is like to be in the trenches with such systems. And I'm excited to share some of these stories with you here today and hope that they will inspire you and think about your own work. My name is Katharina Probst. Thank you for the intro. I, until very, very recently, was a director of engineering at Netflix, working on production systems. I very recently joined Google, where I'll be working on Kubernetes and leading part of the Kubernetes effort. So let's talk a little bit about, let's set the stage a little bit. So over the last few years, if you're following industry chatter and trends, you've heard a lot of people talk about breaking down the monolith. Have a lot of you heard about that? Yes? Okay. So there are many ways to break down a system into different pieces. Oftentimes when people talk about breaking down the monolith, what they mean is you have a big, gigantic system, and you break it into smaller pieces. So then you have smaller pieces of functionality, and then you fit them together to create your user experience that you wanted to create in the first place. So you might ask, why even bother to take something that's big and then turn it into little pieces just so I can put them back together and create exactly the same experience that I had before? So we'll talk about that a little bit. It is important to note that there are different ways of distributing your computing, right? So if you have one app and you run it horizontally scaled, meaning you run many, many copies of it, that's another way of distributing your system. And most of the, or much of the time, both of these happen at the same time, right? Most systems, or many systems that I've seen, both have horizontal distribution as well as breaking down the functionality into multiple pieces. So it's important to think about those together and the kinds of complexities that you have with that. So that's what I'll be talking about here today. So let's go back and think a little bit about why even bother. This whole distribution thing sounds complicated. Why should I even bother with it? Why not stick with the simpler system? I could go on for hours about complexity of monoliths, and some of you may have experienced this too, but I'll just share a few stories. One of the systems that I worked on not too long ago was a service that functioned in the context of a large microservices architecture. In other words, it was one of many microservices that powered the user experience, right? But that service that my team and I owned was so large and complex that in a lot of ways it really behaved like a monolith. It had thousands of libraries that we were embedding. Most of them were not written by our team. It had server-side scripts that were written by other teams, by client-side teams. So for instance, the team that, the iOS team was writing server-side logic that we were actually operating for them. And it was constantly evolving, right? So there are a lot of things that we learned about what it's like to operate such a system. And the biggest takeaway for me really was complexity makes it super hard to reason about a system, to debug it, and to evolve it. So, for instance, when you have a very large, complex system or app, it's very difficult to reason about the code paths that get executed. And what I found is that the more complex your system gets, the more likely people are to stay away from cleaning up tech debt. I don't know if you've experienced this, but if you have a very complex system and it works, then people are pretty hesitant to touch it and say, you know, clean something up, right? So of course that creates that negative feedback loop where all of a sudden your system is already complex. Now we're not cleaning up the old stuff, and now we don't necessarily really understand it as well as we'd like to. So for instance, in this one system that I worked on, we found a code path that was just eating up a lot of CPU, like a lot. And we spent quite a bit of time digging into this, working with the other team who was actually providing the library where this specific code path was being executed. Turned out that this code path hadn't been necessary in about a year. It wasn't actually doing anything useful. All it was doing is like spinning CPU cycles. So it's good that we found it, and it's good that we were able to remove it. But there are some lessons in there, right? There are some lessons about, well, the more complex it gets and the less likely you are to clean up tech debt, the harder it becomes. Similarly, especially when you're working on a system where much of the code is supplied by other teams or even other companies, it's hard to debug, right? So, for instance, what happens if you have a memory leak? Okay, so you have a memory leak, maybe your app has no process isolation, it's just all running together in one process. It's difficult to figure out where that's coming from, right? And then finally, what I put up here is it's hard to evolve such systems. The situation we were in, the system, we wanted to evolve our code, and also all of those other teams that were providing us with libraries that we embedded were evolving their code constantly. So imagine you have an app that you're responsible for, and you have, I don't know, 500 libraries that you need to embed that have their own transitive dependencies, and let's say 50 of them a week change, right? And you want to push out the code, and your team wants to get out their code, and these other teams want to get out their code and get it to production. So you're going to end up spending a lot of time finding sort of the magical combination of dependencies and transitive dependencies versions that work together fine. So you need to do 4 things. You need to be able to build the thing, which is not always easy if you have that many dependencies. You need to be able to pass your tests. Hopefully you have a lot of tests, unit tests, integration tests, all of these things. It needs to pass all of those. It needs to pass a canary, so putting it in front of a small portion of users and making sure your metrics look fine. And then it needs to hold up in production in front of all your users, right? I've seen it go wrong at all 4 of these. And so it just puts you in the situation where it's difficult to evolve such systems. So in this particular case, that system I worked on, we actually did end up breaking it down into smaller pieces, and that's helped a lot. Going back to, again, we're talking about why would one break down a large system into smaller pieces. First thing is complexity. Second thing is just simple scale. Simple. Nothing about scale is simple, really, but in many cases, scale will force you to distribute a system. So there are many reasons this might happen. Your data may not fit anymore in one place. You may have more requests and more users than you can handle in just one app. So then that would at least be horizontal distribution, like I talked about before. You might also be in a situation where you have different kinds of users in different parts of the world, and their usage patterns are very different, and so that puts you in a position where your app is very difficult to, where it's very difficult to predict the behavior of your app, and it's just much simpler to break it out into multiple pieces so you can reason about it. So all of these things will at some point put you in a position where you're going to want to break it down, potentially. And then the third thing is reliability, right? Something that I personally feel very strongly about. There are a lot of reasons for why you don't want to have a single point of failure in your system, right? Single point of failure meaning if that thing breaks, nothing works anymore. If you have your app running on one machine or your data is in one place and that is not accessible, that's not good for your users, right? So there are many reasons that will point to, okay, we'll break it down, we'll scale it, we'll run it in different regions, all of these things, so that we protect ourselves against problems in our own system. And I'll talk more about that later. So, in other words, there are good reasons for why you might want to break down your system into multiple pieces, into microservices, and or scale it horizontally, and or distribute your data and shard your data. So if you've heard me talking over the last few minutes, you're like, okay, so microservices solve all our problems, right? As many of you know, that is not the case. So the real way to think about, the way I think about this, let's put it this way, the way I think about this is there are many reasons why it might be the right thing to do to break down your system into multiple pieces. That does not mean that all of a sudden everything will be simple. It might still be very much the right thing to do, but you need to be prepared for the other challenges that come with it. So let's talk about that a little bit. How many of you heard of the fallacies of distributed computing? Not that many. Great. Look it up. There's a lot to learn there. LP Deutsch put out these fallacies of distributed computing a while ago. And what these fallacies are essentially statements that people may assume are correct, but that aren't. And the reason that people may assume they're correct is because almost all the time, they actually are correct in the sense that your system behaves this way, until it doesn't and spectacularly fails, right? So I would strongly encourage you, if you haven't read about them yet, there are some really interesting stories there to learn. I don't have time to dive into all of them today, so let me just dive into a couple. So one of the fallacies of distributed computing is that the network is reliable. The key difference between having one app that's a monolith that just runs on one machine or instance and having it distributed is that now you have machines talking over a network, right? And one of the fallacies of distributed computing is that the network is reliable. Let me tell you, it will fail at some point. So let me talk about that a little bit. And let me actually broaden this a little bit and talk more about in an architecture where things are distributed, you're going to have cases where one instance sends a request to another instance and expects a response back. And sometimes it will not get a response, or it will not get the response that it expected. Let's talk about that a little. I put up here a very simplified architecture where we have a hypothetical application that gives the user a list of photos and displays it in a grid, say. So the way this will work is that the user sends a request from their device, from their phone or whatever. The request goes through a load balancer. It goes through a front-end server that essentially farms out those requests. And then their request will go to a service that we'll call list of photos, right? So as you see up here, I made all of them horizontally scaled, so all of these pieces work on, across many machines. And that list of photos probably, more than likely, is backed by some data somewhere, right, and might call other microservices, but we don't have to worry about that right now. So almost all the time, the way it works is that your user sends a request, it hits one specific instance on the load balancer, one specific instance on the front end, and one specific instance in our service of list of photos. That's great. And then gets a response back, and the response is displayed to the user. Now, what happens if the front end doesn't get a response, right? So this will happen, inevitably. The front end sends a request into the ether, gets nothing back. At some point, this will happen. Now, what's tricky about this is the front end has no clue why it didn't get a response at this point in time, right? It's like me sending an email to somebody and expecting a response. I send off the email, I get no response. I don't know if the other person got the email. I don't know if they're ignoring me intentionally. I don't know if they're underwater. All I know is I didn't get a response, right? So option 1 is the request never made it to the service. Option 2 is somehow the response was interrupted. That might be a network problem, it might be some other problem, right? And option 3, and that's where I'll broaden it from network failures to more general failures, is that service is actually underwater for whatever reason. So, for instance, maybe the team responsible for it, excuse me, pushed some new code that was bad, and now all of a sudden the system is failing. And it can't respond, and it can't actually, compute your list of photos and return it back. The front end doesn't know that, right? It has no idea why. Now, why is that important? That is important because now the front end needs to decide what to do. The front end can decide to just send an error to the user. It can decide many things. But because it has limited understanding of what's actually going on behind it, it doesn't have full knowledge of what its options are and what the best option is. So often what we do is we retry. So the way this works is that the front end sends a request to the list of photos, doesn't get a response, sits around a little bit, waits, okay, I didn't get it, my request timed out, I'm going to try again. And now if you architected this in a way that is load balanced nicely, now the second time you will hit a different instance on the list of services, list of photos service, right? And you may well get a response. And everything will be great because maybe only this one instance was being slow for whatever reason, and the user gets their answer. So that sounds great, right? And a lot of apps live on retries. There are several problems with retries, but there are two that I'm going to talk about here. The first one is idempotency. So, you send a request, you get a response, or you get no response. You're like, okay, I'll try again. That works fine if, for instance, perhaps you're retrieving a list of photos. What if it's a credit card transaction, right? So if you've booked a flight recently or, I don't know, bought something online, oftentimes you get this little thing on the screen that say, do not refresh your browser for whatever you do, don't refresh your browser, right? What's going on under the hood, of course, is that if you refresh your browser for all intents and purposes, that's a retry, right? And then you have 2 airline tickets or 2 of whatever you bought. So that is not an idempotent request. So we have to be very careful about where we apply retries. There are ways around this. There are workflow systems that let you manage this kind of thing. But we do have to think about this. Now, you may well say, okay, well, sure, credit card transactions, I get that. Don't retry, understood. But what I will tell you is that, I don't know what your experience is. In my experience, it's actually more difficult than you may think to know what requests are idempotent and which ones are not, right? So, for instance, you might have a request that sends a search query and then returns results, right? So you may think, okay, that seems totally safe to retry. Doesn't matter how often I search, I just get a response back. But what if under the hood, whatever service you're calling is writing out those search queries and doing some business analytics on it? Like, what are people searching? What should I be selling more of? Things like that, right? So it's actually worth digging into which requests are safe to retry and which ones aren't. The second problem, so I said there are 2 problems with retries that I want to talk about. The second one is that retries can cause downstream problems for your system, and I will talk more about that later on. To set the stage for the next topic, so we talked about, there are 8 or so fallacies of distributed computing. We're going to talk about 2. We talked about network failures. And next, we're going to talk about topology. So when you have one monolithic app that's running on an instance, your topology is pretty simple. You have one app running on one instance. When you have a distributed system, all of a sudden you have this grid, this network of things that all talk to each other, right? And one of the fallacies here is to think That is fixed. Like, I know my architecture, I understand how the requests flow, that's how it works. In reality, your topology will change. And there are many reasons. Some of them are intentional, some of them are not intentional. So for instance, on the intentional side, you might be all of a sudden have an influx of new users, which is wonderful, right? But now you have to add more instances to handle the load. That's good. So that's manual scaling, but it means that your topology has now changed and you need to be able to handle that. For some apps, it makes sense to have auto-scaling. So for instance, if you have traffic that comes and goes over the course of the day, so as more traffic comes, you add more instances. As traffic goes away, you take them away. This might make sense, for instance, if you're running on a public cloud and you don't want to be paying for those instances while they're sitting idle. But again, that means a change in your topology. If you're constantly evolving your system, you're going to add new services, right? Like whole new functionality, whole new service to your topology. And you need to be able to handle that too. And another example is you might retire services. That is a great thing, right? We talked a little bit about tech debt and how people stay away from it the more complex things get. If you manage to retire entire services because you no longer need the functionality, that is a wonderful thing. But again, you need to be able to handle it. So that's intentionally. On the unintentional side, all kinds of things will go wrong. I spent the last year working a lot on reliability in a pretty complex system. Let me tell you, like, it all happens. Instances fail all the time. Like, if you have hundreds of thousands of instances running, it's just par for the course. Instances fail all the time. You get instances that are overloaded. Maybe you have hotspots in your database. Maybe you didn't shard your data in a way that's ideal. Get hotspots. For many different reasons, you can get overloaded instances. You can get zonal or regional failures. So in our case, Netflix, and other companies do this too, runs in multiple geographical regions, right? Runs their entire stack in multiple geographical regions. And it can happen that one of these regions or availability zones dies, right? Or has some sort of problem. How do you handle that? That is certainly a topology change, right? And then another example is microservices failures. We touched on that a little bit earlier when I was talking about what if your service, for instance, has a bad code push or can't be reached over the network or something like that. And that creates an entire failure of a microservice. So the point of this is you need to be able to think about all the things that might happen and then prepare for them as much as you can. Let's talk a little bit more about microservices failures. In this case, I put a little twist on our example from before, and I said, okay, so in this case, we actually want personalized photos back. So I log in, I want my personalized photos for my search query, say. The team that is responsible for personalized photos just pushed an update, and the update that they pushed had bad data in it, for instance, or a bad config, or bad code. And they noticed as soon as they rolled it out, wow, really, my service is returning nothing useful, right? That happens, right? So then the entire service is out. That happens. Luckily, that doesn't mean that your entire, because we're not in a monolith right now, it doesn't mean that your entire system fails. It means that this one service fails, right? So that's actually better. But you still need to be careful. So we talked a little bit before about retries. So a lot of systems do retries. I've certainly written systems that do a lot of retries, hopefully with exponential backoff, but still, you retry, right? Like, you don't get a response, you wait around a little bit, you try again. What happens if you don't do this carefully is you get the thundering herd problem, or we call that sometimes a retry storm, right? So Right now, there's one instance sitting here that's like sitting on a whole bunch of requests that it got from a bunch of users, and it's not getting any responses, and it retries. And so it's basically putting triple or quadruple the load on this personalized photo service that's already underwater, right? So that's not good. So then things stack up more, and more retries come in. So at some point, the next layer retries, maybe the user even retries, and next thing you know, everything is just blown up. Right? So that's not great, because one of the reasons that we wanted to break down our system into multiple pieces of functionality is that if one part of the system fails, the rest of the system doesn't blow up, right? That was the whole point. But if you're not careful, it could still do that. And I've seen it happen. Now, what do? There are a number of different things you can do. One of the things that I've seen a lot of people employ, we did this at Netflix a lot, is you have fallbacks. So if the front end here notices that it's not getting anything from personalized photos, again, my front end has no idea why. Doesn't know why. That's okay. It retries a little bit, maybe gets nothing, and it realizes that nobody's getting anything. And then it flips a switch and says, okay, no more. I need to give this personalized photo service some breathing room. I'm not going to send any more requests to it. Instead, I'm going to send fallbacks, right? So in our hypothetical case, that might be unpersonalized photos, right? So they're not personalized for me, but I, as the user, still get something. I get a degraded experience, but I still get an experience that works and that is useful to my users, right? That is a very powerful technique that has gotten me and my teams out of trouble many more times than I can count. We can talk for hours about this. There are some drawbacks, and there are some things you have to be careful about what can go in a fallback. But it is a very powerful technique in avoiding this, cascading failure scenario. Another powerful mitigation technique is if we have now, again, our situation of our personalized photos thing is in trouble. There are many cases where that might happen only in one region or zone or whatever failure domain you have. Let's talk about region. In our case here, we're actually running the entire stack in two regions, region A and region B, right? If my personalized photo service is in trouble only in one region, then I actually have a lot of options, right? So what I can do is I can route traffic to the other region, and the user will not notice anything if I do it right, right? So that sounds simpler than it actually is in practice, but it is an incredibly powerful technique that we've used a lot. There are two things you need to be careful of. So one of the things you need to be careful of is you need to be thoughtful about when to fail over traffic from one region to another, in our case. For us, this was always a determination of, do we have confidence that the problem will not follow us to the other region, right? So there may be many reasons why the problem might follow us to the other region. In our case, if we pushed a bad update, and that's why the service is in trouble, maybe that update is part of an automatic delivery pipeline, and in half an hour it's going to go to the other region. Well, that's not great. Now I failed over traffic, and then everything's great, and then 20 minutes later it blows up too, right? So you need to be thoughtful and careful about when to employ this technique. It's an incredibly powerful technique, though. Another thing you need to be careful of is how to fail over the traffic. So, if you have millions of users, a lot of traffic, your stack in that other region might be scaled to handle whatever traffic it normally handles. And now, if you flip a switch and you just send it twice the amount of traffic, say, it's going to die. Like, there's no question. It's just going to fall over. So you need to make sure that you don't do that too fast, or you scale so that it could handle that traffic if you were to send it there. When I was at Netflix, we were working on this system, to fail over traffic. One of the things we did is we, because we auto-scaled over the course of the day, we predicted on an ongoing basis how much capacity we will need in the other region to handle a traffic failover. So that's a very powerful technique, but it's something you have to think about. Okay. Of course, another thing to think about that I just kind of glossed over is you need to make sure that the thing in the other region actually works. And one of the big things, it needs to have your data. So if I, as the user, get failed over to the other region, and the other region has never heard of me, then that doesn't really help anyone, right? So those are the kinds of things you need to think through. So I hope I've given you a little bit of a flavor of the kinds of things that, the kinds of complexities that come with running a microservices architecture, horizontally scaled services. I think the important thing for me to take away from all of this is that there are a lot of learnings here that can really help make this a lot easier, right? Is it complex and complicated? Are there a lot of things we need to think about? Absolutely. There are with monoliths. There are with microservices. There are a lot of things we need to think about. I find that endlessly fascinating, but I also want my users to be happy, right? So it's not, in my mind, it's not gloom and doom, right? It's not a bad thing. We just need to think about these and solve these challenges so that our users can get the experience that we want them. So in this last part of the talk, I'm going to summarize some of the learnings that I took away, some of the things that I learned over those years working on those systems, and we use and use successfully. The biggest takeaway for me has been don't assume, and that's kind of the point of these fallacies of distributed computing, right? Is don't assume that everything will work as expected, right? Things will break. If you run hundreds of thousands of instances, one of them will fail. Many of them will fail. You will push back code. You will push back config. Your network will fail. These things will break in all kinds of obscure ways, and that's okay. So don't assume that everything will always work the way that you planned it and the way you expected it, and embrace that. And then prepare, right? So what that means is I am a big proponent of investing very heavily in insights. So monitoring tools, lots of metrics and logs, and lots of meaningful alerts, right? So, I don't know how many of you have experienced alerts that go off 10 times a night, you just start ignoring them, right? So, but investing very, very heavily in insights, in my mind, is critical because something will break, and it will be obscure, and it will be something you've never seen before, hopefully, because if you see the same things all over and over again, that's not great either. So in those cases where something will break, you want to be in a position where you have all the tools and metrics needed to figure out what's going on and to figure out what your best mitigation strategy is. So I think that's a good idea. Know your weak spots. So one of the things I learned is that when you work on a complex system, it is worth investing in understanding as much as you can about the system, right? So that means insights, but it also means just understanding where your weak spots are. Every system has weak spots, right? So there might be tech debt that you just haven't gotten around to fixing, but for sure will in 6 months, right? There are maybe cases where you have services that are frequently underscaled, and you're surprised by that. There might be services or devices or clients that aren't handling failures gracefully, right? So maybe if they get an error from the server, they don't handle it gracefully and the entire app dies. So spending time understanding your system will always pay off in my view. And then, of course, fixing those weak spots where possible. I don't pretend that I've ever worked on a system that didn't have weak spots still. I think that's normal. But I think understanding them and fixing them where possible will pay off. I talked a little bit about understanding what's idempotent, what requests you can retry. That is also important because it will allow you to, again, employ mitigation techniques such as retries that can really help your user experience and the stability of your system. So the big takeaway is learn as much about your system as you can and don't assume that it will always work as expected. And then part of that is also to test realistically, right? So of course, everybody knows that in theory we should write unit tests for everything and integration tests for everything. I've yet to work on a system that had had the coverage that we wanted it to have in terms of testing. But we always try. That's important, and that is, that will catch so many things before they go to production. That's great, and we should do that. I think there are also cases where you cannot catch things until they go to production. And part of the reason for that, and this is controversial in some circles, is that if I have a test environment, that will teach me some things about how the system works. I also have a production environment, and in that production environment, I have 1,000 times the scale or 10,000 times the scale that I have in my test environment. So it will behave differently, right? There are things you're not going to catch necessarily. So for instance, your timeouts might not be configured properly, adding up all the ones, through the call stack. There are a bunch of things that you're going to find out by testing very carefully in the production environment. So you may have heard of chaos testing. Chaos testing is the discipline of essentially intentionally introducing failures into your production system to understand how well your production system will hold up. So, for instance, the most famous thing in this context maybe is Chaos Monkey. Chaos Monkey goes around and randomly kills instances in your system, right? And then in your production system, right? And then you understand, okay, what does my system actually do with that? Can it handle those kinds of failures? Load testing is another one, really understanding, and you don't have to do that in production necessarily, but really understanding what the breaking points of your system are. And then finally, as you push out code to production, or config or data out to production, run canaries, meaning like try it on a small percentage of users in the context of your big production system. All those things will catch things that you wouldn't catch otherwise. So now you spend a lot of time understanding your system and invest a lot in understanding your system and having insights. Once you have that, you can think about what are my best mitigation strategies? What are the techniques that I can use to get me out of trouble? So that's what I call building defenses. So when I think about building defenses, I mean building things that are mitigation strategies that are as general as possible. Right? So we talked about fallbacks. Fallback is really a concept, right, that can be employed for a number of different failure scenarios, right? So if I have one service, that service could fail for a gazillion different reasons, right? But my fallbacks are one strategy that I can employ for all of them. And that's great, right? So I have something that will get me out of a lot of different kinds of trouble. Similar with traffic rerouting or traffic failover, regional failover. It doesn't really matter what's going on in that region. All I need to know is it's in trouble and the problem won't follow me if I fail over traffic. That is a wonderful mitigation strategy that can help me get out of trouble, again, out of lots of different kinds of trouble. I put another couple of things up here. So, for instance, rollbacks, being able to roll back quickly. What I mean by that is if you push out a new version of code or config or data, the ability to move back to the last known good state very quickly is, again, a very general strategy that can help you in a lot of different cases because lots of different things can go wrong when you push out new stuff. There are a number of others, selective throttling, being able to turn off tests very quickly, all kinds of things. But think about the strategies that you can have that are the most general that will get you out of trouble. And then finally, one of the things that I've always, when I work with other teams at Netflix and at Google, make changes gradually. When you roll out changes to code, changes to config, changes to data, you should test it, absolutely. We talked about that. You should test it and make sure that it works as much as you possibly can. And yet, you will miss some things, right? So one of our best strategies in keeping our users out of a bad experience is to make changes gradually. I cannot count the number of times that we rolled some change out that passed all our tests, passed our canaries, everything looks great. We roll it out to one portion of the users and it blows up, right? It just happens. And so one of the things I am a big proponent of is make changes gradually. So that could be zone by zone, or region by region, or device by device, or portion of user traffic, percentages, whatever it might be. Whatever works for you, but do it gradually. And for us, gradually meant, do it to one region. We had 3 regions, do it in one region, wait an hour, and then go to the other regions. That's not that slow, right? But still, it prevents so many problems. So that's a very powerful technique. And what's really important about that is, I touched on that also with gradual traffic rerouting. Same thing. It's like, do it gradually. Don't overwhelm your system. What's really important about this is it doesn't matter if you roll out your changes gradually if you don't actually watch the metrics and you don't actually watch what's going on with your system. It helps nobody, right? All it does is it slows you down and slows everybody down, right? So it needs to be paired. Making changes gradually needs to be paired with great insights and great alerts, right? We need to know how is the system actually behaving with this new stuff, whatever the stuff is, code or config. We need to know, we need to be able to compare the before and after and make sure that it actually works, because that is the whole point of making changes gradually, right? So understand your system, test, build great defenses that are as general as possible, and make changes gradually and watch your metrics. So those are for me, those were probably the biggest learnings over the last few years. So with that, I'll open it up for questions, and thank you very much for your attention.